For our last video in section 6.8, we look at the topic of indeterminate exponents or powers. So we listed three possibilities in the previous video, where it could be something like 0 raised to the 0, infinity raised to the 0, or 1 raised to the infinity. And here, similar to how we tackled products, we're going to use algebra to help us kind of simplify what's going on with this. So if we think of this like two functions, where f is the base function and g is the exponent function, then still our goal is to see what we can do in terms of getting this eventually to L'Hopital's form. And this seems kind of far away from the goal right now, but maybe one thing we can do is, what if we consider naming this expression? Let's call it y. So typically, whenever we want to get rid of exponents, or at least move them out of the exponent and in line with other parts of the expression, well, we take a log. If we were to take a natural log of both sides of this equation, then the one side would be natural log of y. The other side, though, remember the property about exponents inside a logarithm multiply outside the front of that logarithm. And we get this expression. G of x will come down and it will multiply times the natural log of f of x. And now we've got a product going on. One expression, g, and the other expression, the natural log of f of x. So depending on what we need to do, then maybe one more step just to get us on the road to using L'Hopital's rule is we use reciprocals. Now we can rewrite g of x as the denominator function 1 over g of x, and the hope is that this thing will be either 0 over 0 or infinity over infinity. And then we can start taking a derivative to see what happens. Now note, whatever result we get from this is not going to be the answer. That's going to be the natural log of y equals answer. So then we need to get back to the original expression, f of x raised to the g of x, to see what that would turn into. So let's jump into an example to see what we're talking about. Here we have the limit as x approaches 0 from the right of x raised to the x. So both exponent and base are changing, but they're both going towards a really small number. And this really is indeterminate because, well, there's kind of two cases. Is the base going to 0 faster than the exponent? And in this case, 0 raised to anything is just 0. Or is the base staying as the variable and maybe the exponent is going faster towards 0? But depending on what that base is, normally anything raised to the 0 power is 1. So it could be either one of these, or maybe something completely different. Thus why this thing is an indeterminate form. So, as we wrote before, let's consider renaming this expression. Let's call it y, and that is equal to x raised to the x. So, we could take a natural log of both sides and get natural log of y equals x times the natural log of x. So the limit as x approaches 0 from the right of the natural log of y is the same as the limit as x approaches 0 from the right of x times the natural log of x. And this is our indeterminate product of 0 times negative infinity. So just like products before, now we choose to rewrite this into a fractional form. And if we recall from what we did before, we let 1 over x be our reciprocal function in the denominator, and we left natural log of x alone in the numerator. And this was still going to be a infinity divided by infinity indeterminate form. So L'Hopital's rule can be applied, and when we take our derivative of both expressions, the numerator just becomes 1 over x, the denominator becomes negative 1 over x squared, and remember how we simplified that expression. When we flip the bottom and it simplifies with the numerator, we just get the expression negative x. So this just goes towards 0. Now, we have to go back a little and remember that this is the natural log of y, not the original expression we were solving for. So let's write that for a second. And now we note that we have to actually solve for y. Well, remember one way to cancel off natural logs in an expression to reveal the inside part is to exponentiate both sides. So as kind of a cruel way to write it here, I could just write an e on both sides to take care of that. And so what the left-hand side simplifies to is exactly that same limit, x approaching 0 from the right of y, and now the equal to e to the 0 on the right, or what turns into the value 1. But remember that y was exactly the stand-in for our original expression that we were finding here, x raised to the x. So that's exactly the problem that we have solved. The limit as x approaches 0 from the right of x raised to the x is exactly the value of 1. So this strategy of using natural log to rewrite the expression is very key. We can't really get away without doing that in this problem. And even more so, after what we think is the end of the problem, after we've used L'Hopital's rule to find the limit, we have to do one more kind of going backwards step of solving for that original expression that we were trying to find on the inside.